So the next speaker is Professor James Tien from Case Western Reserve University. He's worked for many years studying material flammability in reduced gravity, and including partial G. So he's going to give an overview of past research on material flammability and partial gravity.
Can you hear me?
Yep.
Oh, okay. I think I'm going to stop the video. You do not want to see a wrinkled face. Okay, and this review will be short, only 10 minutes, but many of the material have been covered by Gary and Paul. Next. Okay, partial gravity basically is the gravity between microgravity and Earth gravity. And I think the terminology was first introduced by Kirk Sexter almost 30 years ago. Okay, now the lunar gravity and the Martian gravity, of course, are special cases. So my talk will be talk about past experiment in partial gravity, use aircraft. And I'm going to touch upon a little bit about simulated partial gravity results in normal gravity environment, and briefly mention direct model simulation and then conclusion. Next. Okay, so we can use aircraft to fly parabolic trajectory. And on the left, you can see this is a trajectory with zero gravity, and you can modify this to be partial gravity. And in the middle, you see the G jitter trace on the 3 axes. And in some axes, it's a little bit more than the other. So if you want to choose a partial gravity, and sometimes you have to choose the best axis. And on the right, you see this is a 0.1 G parabola. You see always some G jitter. Okay. Now, so the restriction of use aircraft is you have G jitter, which is of the order of 10 to the minus 2 G. So if we use in partial gravity, it has to be significantly larger than this G. So probably a cutoff will be 0.1 G, and that give you a 10% error. And of course, you are also limited by the time, which is of the order of 20 seconds. Next. Okay, so here is Kurt Sexter's work. Okay, and on the right, you see a color shadowing picture of the side view of the flame, and at 0.1 G. Okay, you can see the flame is significantly thicker, and the standoff distance is larger. Okay, and on the left, you see this flammability map, and with oxygen and the G as axis. And on the 1 G is 10 to 0, and on the left I have a high G, which is come from 1 G centrifuge. Okay, and you can see the black portion are burning, and the open portion are the extinction. You can see at lunar gravity, the oxygen is lower than at 1 G. Okay, that's significant. So basically, okay, another thing, Kurt's experiment is on using Kim wipe, very thin paper, because that give you a fast response. You only have 20 seconds. Okay, so we find LOI, the limiting oxygen index in lunar gravity, is less than LOI at Earth gravity. That's probably the most significant of his work. And in the middle, you have flame spread versus G, which shows the opposed flow. It is downward spread. It's not terribly sensitive to G level. Next. Then Young Fair doing another experiment with upward spread, and this is on 2 centimeter wide Kim wipe at reduced pressure. Okay, and the narrow sample and the reduced pressure make it possible to see a flame where its limiting length is limited. In other words, the upward spread was first going to grow and then stop at certain height. Okay, and that's constant flame length. And so this is called steady spread and constant flame length. And we can do that with reduced pressure and narrow sample. And if you look at some of the figure, and the left one is the side view of the upward case at different gravity, okay? And the second one from the left is downward, okay? And I would forget about the others. We'll see that later. Okay, next. Okay, so on the top left is a infrared picture of the flame. Okay, and the next one is a model. Okay, which has temperature, and the temperature 1 is 300 degrees, and the down left is the comparison of surface temperature. So the model is actually reasonably good. On the right, we see, okay, this is a gravity versus pressure. Everything is done at 21% oxygen. Now the downward case, you can see we have a shape which is similar to the oxygen versus G. Okay, again, and the lowest G is not on Earth. Okay. And this is what somewhat expected. The upward case is a little bit surprising, and it's sort of monotonic, but I have some sort of reservation on how difficult it is to obtain upward spread limit. So we will come back to that later. Okay. Next. Now here is the spread rate, upward spread rate. Okay, and the upward spread rate, if you look at the curve, its upward spread is increased almost linearly with gravity. Okay, and you have seen some open symbols there come from the model, which is reasonably good. And as you can see, the downward spread is lower and has a peak somewhere in the gravity level about 0.3 or 0.4. Okay. Now, this is a function of pressure. In the inset, you can see at a different pressure, you have different spread rate. All of them increase with gravity in the upward spread. Okay. Next. Okay, we see this kind of picture before. Okay, so we get a lot of data which is at reduced pressure and at the lower pressure. So I think in the work by Julie Kleinhans, we're trying to see, hey, can we get any correlations? And the starting point is Grashof number, because Grashof number tell you the buoyancy boundary layer, which we thought was control the upward spread. Okay, so if you look at the Grashof number, if you look at the definition, you can find out if you want to keep the Grashof number constant, if you keep G over P square constant, the Grashof number is constant. If you just change pressure and gravity in such a way as P square G, Grashof is non-constant. So this is a demonstration. On the left, it's same pressure, 3 different gravity, lunar, Martian, Earth, and clearly the Earth is longest. Okay. On the second graph, this is top view, just seeing the paralysis length, and we make P 1.8 G constant. Now we will talk about why P 1.8 G versus P squared G. Almost constant. You can see the paralysis length is almost constant. Okay. At the 3 different gravity. On the right, this is a side view. It's a side view. Okay, side view of the flame. Okay, you can see the flame separate. The standoff distance is also almost constant. Okay, flame length and the standoff distance is almost constant. Next. Okay, so the spread rate at 3 different gravity level, Earth, Martian, Lunar, are clearly different. Okay, but if you're trying to correlate, you can plot everything on the upper right graph, okay, using P squared G. That's what we started with. You look at this curve looks pretty good, but if you look at one graph down, you find if you're trying to plot each one of them, lunar margin, you see a systematic error, deviation, okay? And that's why Julie ended up using P1.8G. Then the thing was correlated, okay? Despite that, we thought this is a very small, a small defect, and it could be because we use relatively narrow sample, okay? So we will still require refer it as square P square of G, okay? But remember, this is the Kim wipe. It's a very simple stuff. It's only for upward spread only. We have no radiation, no kinetics, and cannot study extinction because the pressure is different. Okay, next.
So one more minute.
Okay, one thing we look at this is if you look at this three frame again, the frame started with a leading edge, and then have a boundary layer type. Leading edge, we're doing is what we call frame stabilization zone. If you do an analysis, you find what is standoff distance over there. It turns out also P square of G. So we are really happy. In other words, you have this frame start with the upstream with same P square of G and extend to the boundary layer. So really feel good. Another stuff is the stabilization zone is the frame standoff distance for downward cases. So for downward spread, P square of G also work. Next. Okay, so look at another configuration, this stagnation point flow, okay, which a lot of people use in combustion. And you have the flow mechanics is governed by the stretch rate, AB in this case. It turns out AB is proportional square root of G over R. R is the radius of curvature, okay? If you go through this process, again, you find inside here is also P square over G. Also P square over G. So we are really very happy. On the other hand, if you want to simulate with this geometry, you have two ways of doing it. One is P square over PG. The other one is P over R. Okay. So you can also change R to simulate this. I'm going to forget about the right. Next. Okay, so there are a bunch of work follow this. I have no time to go through. Next. So I'm going to comment on numerical modeling. It turns out numerical modeling, and I'm going to concentrate numerical modeling for upward case, okay? And the detailed numerical modeling has a potential to extend 1G to 0 to lunar G and or to other G, okay? If you look around the first work by Jiang, it's on two-dimensional study. And then she extend this to have different boundary and with pressure. And then we have 3D with steady. Finally, we have 3D unsteady, okay? And the model have a lot of detail, okay? And the right, you can see this is a model with different G for candle flame, all the way from 0G to 30G, which flame is monotonic, not monotonic in term length. Next, conclusion. Okay, we know material flammability, the data is very limited in partial gravity just because of very limited test opportunities, okay? Now, existing data suggest wider flammability limit for downward spread at reduced gravity. And then I think this is using very simple solid. It needs to be extended to practical material, okay? I think more work will be needed for the upward spread limit, okay? Pressure modeling should be a very useful tool to evaluate the frame spread rate, okay? This also should be extended to practical material. The pressure extinction limit need to be studied more. it turns out pressure limits not only depend on kinetics, but also may depend on the flame configurations. There's a difference between stagnation point flow and side stabilized flow, such as flame spread. Detailed modeling can be a powerful tool, but in order to be really useful for NASA, I think we need to extend this to have more complex pyrolysis for charring fuel, which probably will be used for the crew member custom and the material. Okay, and the unsteady three-dimensional model is also appropriate to model NASA 6001 case, and it can be extended to reduce gravity. Thank you.
Thank you, Professor Tian.